Hello, BC Calculus. I am Nate Wygen, an apprentice of Mrs. Greenman and her great knowledge of calculus. If you haven't noticed already, I am dressed up a bit, not because BC Calc is a formal event, but because I am about to graduate. But the problem is that I haven't completed my calculus training. So today, with the help of my fellow BC Calc students, we will be teaching you all about the calculus of parametrics and applying that calculus to real life. But before we dive right into the calculus, we need to learn the background of parametrics, the pre-calculus. So I am about to hand it off to Mr. K's student, Rorie Simpson, to help you to refresh yourself on the pre-calculus of parametrics.
Alright, so intro to parametrics. This will just be a little bit of review from pre-calc. So first, what are parametric equations? So typically, when we see equations in math, there are two variables. So it'll be like something like y equals mx plus b, or y equals x squared, or y equals x squared plus 1. But in a parametric equation, there's actually three variables, and the third one will relate relate to the first two variables. So it'd be like y equals f of t and x equals g of t. So I have an example here of how you would convert a parametric equation into a rectangular form equation, which is what we normally see. So if you had x equals t minus 1 and y equals 2t plus 3, first you would solve this one for t. So then you can just take that and substitute that in for the t in the other equation, and then as soon as you solve that, then you have a rectangular form equation. And you can basically follow that process for the easier problems. So for this one, it's another pretty easy one. So you have x equals 2t minus 4 and y equals t plus 1. So first you want to solve, you want to solve for t in one of them and then substitute it into the other one. So I'd pick x equals 2t minus 4, just add the 4 over, divide by 2, then you have t by itself, substitute that in over here, then you have x plus 4 divided by 2 plus 1, simplify that, and you have y equals 1/2 x plus 3. And there it is. You can do this for seemingly more complicated one, but it's really not that more complicated. So you could just get this one in terms of t, so t equals x minus 5, then put that right in here, and it's x minus 5 squared. Y equals x minus 5 squared. And then you could throw in some coses and sines, and when you see cos and sine, you just have to think of all the trig identities, and then that's where you just try to isolate the cos or the sine. And so for this one you divide by 2, for this one you divide by 4, and then right here you'd notice that you have cos by itself and sine by itself, and then that's where it should click. Oh, sine squared plus cosine squared equals 1. So the key here is to just remember your trig identities and try to relate that to what the equations you're originally given. So you can just plug in x divided by 2 and square that, and then y divided by 4 and square that, and then you end up getting an ellipse. And then you can graph it, and then there's going to be restrictions also because of the original equations you got. So cos can only go from -1 to 1, and you multiply that by 2, so it's -2 to 2. And sine can only go from -1 to 1 also. You multiply that by 4, so then it's -4 to 4. And then here's another one with a trig identity. So right off the bat, it might not be obvious, but the identity you need is cos times 2x is equal to 2 times cosine squared x minus 1. So then right here, you already have the cos t. So you're just going to plug that in for the cos t squared, and then just square what you have here. So it's going to be x squared, so it's y equals 2x squared minus 1. And then the restrictions would be on x, where cos can only go from -1 to 1, so that's the restriction. And then another trig one right here. So right off the bat you see secant and tan, so it should click that 1 tan is secret. So this is a fairly easy one. You don't really have to plug in much. Just put the y here, put the x here, and 1 plus y equals x, then simplify. Put it in standard form, y equals x minus 1. And then for the restriction, it's a little bit different. Secant squared can only be greater than 1 or equal to 1, so that's the restriction. And then another one, right off the bat, you don't see any trigonometry, so you just start to solve for t. You get t equals plus or minus radical 2x. You can just plug that straight into here. You get y equals 1/4 radical 2x cubed. And then simplify that and you get this, and the restriction would be on x, and you see that it would have to be greater than 0 because t squared has to be positive and it's multiplied times 1/2. So then, after seeing that, the general steps for converting a parametric equation to a rectangular equation would be, first, to choose one of the equations and solve t for it. If that's easily done, that's obviously not with the trigonometric questions, and then just substitute that into the other equation. And then again, if there's any trigonometry in it, just look for an identity and then substitute. And another use of parametric equations would be projectile motions. So you express projectiles in terms of an x equation and a y equation, and those are related by time. So the x movement relates to time, and the y movement relates to time. And usually in the y portion, there would be a gravity, maybe air resistance could be in the x as well, wind. All those things can take a factor and affect the equations. And then when you combine these equations, you can find multiple values such as time in air, range, and max height. So for the time in air, you just have to figure out the second time that y is at 0. So obviously it'd be at 0 here, and then you find out the second time it's at 0, solve for that time, and that'd be the time in the air. And then the range, you take that time that it was in the air and just plug that in for t in the x equation, and that'd give you the range of how far it traveled in the x direction. And then for the max height, that'd be halfway through if you look at the shape of what a curve would be like, it'd be halfway through the flight. So you just plug that time in for y, and you'd find the max height. And then there's also circular motion that can be demonstrated with parametric equations. Obviously, just a plain circle, center at 0. Notice how if the center changes, you'd see a number added in front or subtracted. But if there's no number, then it starts from the center, and then the coefficient in front of the cos of the sign would be the radius. And then obviously right here, like I mentioned, that's how you change the center with the h or the k, and then again the a would be the radius. And you can also look at ellipse. When the coefficients are different, then that's a sign that it's an ellipse. And then you just solve, and then so you divide the a over, it'd be x over a, and then you look at this identity. You'd have to square it to put it into the identity. You do the same for this bottom portion, and then you end up with this generic form. And now for the last one would be a hyperbola. That'd be when a is greater than b when you solve this, and then again divide the a over secant squared tan squared, sec minus tan squared equals 1. Just plug these in, plug this in here, and then you get that, and that's the generic form. And that's about it for the pre-calc review for parametrics.
They do say that the hardest part of calculus is remembering what came before. Thank you, Rorie and Mr. Martin, for that pre-calc. Now, some calculus. Kyle Norcross will be teaching some important information on the first and second derivatives of parametric equation.
Okay, so now that we have gone over the pre-calc of parametrics, we're going to move on to the calculus of parametrics. So finding the slope of a parametric equation is more difficult than a regular function because it is not actually a function. You can't look for the derivative defined at p because there are multiple different slopes. Here, here, and here. So in order to find the slope, you have to cut the curve so the area around p becomes a function from a to b, and then you would get a function y equals big F of x for t that is on the interval from a to b. So then if we rewrite this with our parametric equations, it would be g of t equals big F, and then you input the x into this. So it'd be little f of t. Then in order to find the slope, we would implicitly differentiate, so g prime of t is equal to big F prime of f of t times little f prime of t. Then we would take that and change it to g prime of t is equal to big F prime, and that f of t can actually be changed to an f of x. Big F prime of x times little f prime of t. And then we would divide by little f prime of t on both sides in order to get the slope of the function. So big F prime of x is equal to g prime of t over f prime of t. And then in Leibniz notation, that would be dy dx is equal to dy dt over dx dt. Okay, so now that we know what the first derivative of a parametric equation looks like, dy dt over dx dt, we're going to move into how to find horizontal and vertical tangents, which will help with graphing parametric equations. So in order to find the horizontal tangent, we know that the first derivative has to equal 0, or dy dx equals 0. So that's only going to happen when dy dt equals 0. And then a vertical tangent is going to occur when the first derivative doesn't exist, or dy dt, dy dx doesn't exist. And that's only going to occur when dx dt is equal to 0. Okay, so now that we know how to find horizontal and vertical tangents, we're going to go through an example. So if we have a parametric equation with x defined as t squared and y defined as t cubed minus 3t, and we're told to find the horizontal and vertical tangents. So first we're going to find the first derivative, so big F prime of x, which is equal to dy dt over dx dt. So that's going to be f prime of x is equal to 3t squared minus 3 over 2t. So we're going to have a horizontal tangent, remember, when dy dt is equal to 0. So we're going to set 3t squared minus 3 equal to 0, or 3 times t squared minus 1 equal to 0. So if we do that, we're going to get a horizontal tangent when t is equal to plus or minus 1. And then if we plug this value back into the y equation, we can find when exactly those points are, which would be at 1, -2, and -1, 2. And now we can move into the vertical tangents. So we know we're going to get a vertical tangent when dx dt is equal to 0. So then we're going to set the bottom of the first derivative equal to 0. So when 2t is equal to 0, which is going to happen when t equals 0. And we know if we plug this back into our x equation, we know that's going to happen at the point 0, 0. Okay, so now we're going to look at how to find the second derivative of parametric equations. So we know the first derivative, dy dx, is equal to dy dt over dx dt. And then in order to find the derivative, we are going to do the derivative of the first side, dy dx, and take the derivative of the other side. And then after some algebra, we're going to come out with the second derivative equal to d dt of dy dx over dx dt. So basically you're going to take the derivative of the first derivative with respect to t over the first derivative of the x equation.
Make sure to write that down. Super important stuff. Thanks, Kyle. Now the moment you've all been waiting for. When are we going to use this stuff? Well, I think Aidan O'Connor has that answer for you.
What is up, BC Calc? My name is Aidan O'Connor. I got my BC Calc 2020 shirt on. I'm dressed for the occasion. So, up until this point, you've probably learned a little bit about parametrics and the calculus of parametrics, and my job is to apply those parametrics to the real world. And so to do that, we chose to use a kick from the one and only Fairport varsity football kicker Nate Wygant. Chose to use a kick from him. So yeah, we got a video. Here's the raw video. Pretty good kick if you ask me. So yeah, let's apply some parametrics to this kick. So in order to do this, I tracked the ball as it went with little dots. Yeah, so these dots are at time increments of like 0.1 seconds or 0.2 seconds. It depended on how lazy I was. And yeah, that's the general idea of what the curve's gonna look like. Unfortunately, this video was shot at not like a perfect angle. Like it was kind of at an angle that makes the parabola a little tilted. So we're gonna work with what we got. That's what the curve looks like. Like when you connected the dots, it's not super pretty. So I, straightened it up, made it look pretty. So that's what the final curve's gonna look like. And so to apply parametrics to this, unfortunately, it's not like one parabola, so we can't just apply one equation to it. So we're actually gonna split it up into 3 sections. You can see there's like a linear area here, and then it kind of turns into like a square root around here, a square root equation, and then it turns into like a parabola. So we're not gonna have 1, we're not gonna have 2, we're gonna have 3 parametric equations to track this kick. So, triple the math, triple the fun. That's how I like to look at it. So yeah, here's our graph. Boom, here comes the curve. So yeah, we're gonna split it up into 3 on this next slide. Here's the first part coming in. Okay, the linear part. Pretty solid line. First equation. It's gonna be x of t equals t minus 0.75, y of t equals 0.8t plus 9. This will be from -11 to -1.25 for the t-values. Okay, let's bring in the second part. This is the square root part. Second equation. X of t equals t minus 2, y of t equals, sorry I can't see it, 0.7 times radical t plus 8 from 0 to 6.5 for the t-values. And then let's bring in the third part. Okay. This is the parabola part. This is x of t equals t plus 4.5. And this is because the vertex is shifted 4.5 units to the right. Same thing for the square root. The vertex of that is shifted 2 units to the left, so you got the -2. And then for the y of t equation, we got -0.16t squared plus 9.8. And this is from 0 to 7.5 for the t-values. So I know what you're probably thinking, right? Aidan, how am I supposed to trust that these are the actual equations, right? And this is BC Calc. I can't just give you the equation and tell you that, that's it, right? So how am I going to prove that? Let's plug in the endpoints of the t-values into these 3 equations. So for the first equation, you had the x equation was t minus 0.75. So we're going to plug in negative 11 minus 0.75 equals negative 11.75. And if you look on the graph here, I'd say it's pretty close to that. Check mark. Okay. Other endpoint, negative 1.25. Subtract 0.75, you get negative 2. Let's go up here. X value, pretty much negative 2. Bingo. Check mark. Okay. Onto the y part, 0.8 times negative 11 plus 9 equals 0.2. Y, yeah, I would say it's maybe a little bit above 0.2, but right on, you know. And then 0.8 times negative 1.25 plus 9 equals 8. That y value is pretty much exactly 8. Check mark. Let's go to the second part, the square root part. This is where you're probably like, Aidan, there's no way that's exactly tracks it. Let's plug in the endpoints here. Again, I can't really see it because my phone's blocking it, but we've got, so this x equation was t minus 2. We're going to plug in 0 for t for the left endpoint, and that gives you 0 minus 2 equals negative 2. Again, right on, check mark. 6.5 minus 2 equals 4.5. Again, if you look on the right part of the graph, around 4.5 pretty much. Check mark. Let's go to the y equation. This was 0.7 times radical t plus 8. So you plug in the 0, which is the left endpoint of the t values, and you get 0.7 times radical 0 plus 8. The 0.7 times radical 0 cancels that, which leaves you with just 8. Again, that's right at 8. So check mark. 0.7 times radical 6.5 plus 8 for the right endpoint, which gives you 9.785, 3 decimal place accuracy. And if you look at the y value of the right endpoint, it is right around 9.785-ish, right around there. So another check mark, bingo. So yeah, those first two are approximated pretty well. Let's go to the third part. Boom, the parabola part. Okay, the x equation was t plus 4.5. You bring in 0, 0 plus 4.5 equals 4.5. Again, check mark. 7.5 is the right endpoint, and 7.5 plus 4.5 equals 12. Right at 12. So yeah, 2 check marks for the x. And then for the y, we got negative 1.6 t squared plus 9.8. That was the y equation. And so negative 1.6 times 0 squared plus 9.8. The 0 part cancels out, so you just get 9.8. Again, it's right around 9.8. So you get a check mark, and then negative 1.6 times 7.5 squared plus 9.8 is 0.8. And if you look at that, it's right around 0.8. So another check mark. Yeah, so feel free to check my math. It all checks out. And so yeah, let's go back. Those 3 equations track the parametric. Those 3 parametric equations track Nate's kick pretty much perfectly. Again, it's an approximation, so it's not exactly perfect, but it's done pretty well. Yeah, so that's all I have for you guys. Thank you for watching. Yeah, have a good summer.
What a kick indeed. Thanks, Aidan. Hope you guys learned something new about parametrics during this video. And if you haven't noticed already, I earned my cap and gown. Thank you to Rorie, Kyle, and Aidan for sharing your great knowledge on parametrics. Also thank you to me for editing this video. And finally, a big thank you to Mr. K and Mrs. Greenman for everything this year. Have a great summer.